Bernd Schroers from the University of Edinburgh, who is going to talk about the dynamics of chiral magnetic skyrmions.
Thank you. Thanks, Teresa. Thanks to the organizers for inviting me. It's been a very interesting meeting. I think this is a very nice set of topics we'll be looking at, including a lot of analysis, but also lots of experiments and phenomena. And my own background is perhaps slightly different from both of these. I'm a mathematical physicist with a lot of interest in geometry, so that's going to be the main angle from which I talk, and I'll be talking about magnetic skyrmions, which I think is a bit of a theme today. So we've got several talks. I'm not best placed to introduce you to magnetic skyrmions. There'll be other people talking today who are better placed to do that, but maybe what we produce as a team is sufficient to give you an overview of what magnetic skyrmions are. And I should say my own background is from nuclear skyrmions, and it's probably worth saying that, of course, the name skyrmion comes from Tony Skyrm, who invented these as a model for nuclear physics in one dimension higher than what I'm talking about today. So 3 dimensions mapping to the 3-sphere. Magnetic skyrmions are in 2 dimensions mapping to the 2-sphere. And that's what I'll be talking about today. And I'll be talking about dynamics. That's what I'm heading towards. But I will need to talk quite a lot about static solutions. And again, I think my sort of take on that may be slightly different from the other talks. I want to show you that this model that describes magnetic skyrmions has an interesting special coupling choice where you can write down solutions exactly, including solutions of arbitrary degree, and that will be quite important in understanding the dynamics. So that's roughly the outline, magnetic skyrmions and this geometrical picture, which are called gauge sigma models. Then I need to home in on a particular point of view that arises from this, which are called magnetic walls and kinks, and then I use that to talk about the dynamics. These are some papers, and I should say the last paper hasn't appeared, but that's with Tom Wynyard, who's also here, and he has got a poster out there which illustrates some of the things and beyond what I want to talk about today. So that's related to what I want to talk about. So just a reminder, magnetic skyrmions are experimentally observed in magnetic materials, certain ferromagnetic materials, and that's now 15 years old. It was known that the mathematical model for these materials has vortex-like solutions. They were called magnetic skyrmions then, but they were only then observed in microscopy from in about 2010. So these are pictures at low temperature, at T 25 Kelvin, and no magnetic field. The ground state of the materials are these stripes, which were interpreted as magnetic magnetization that spirals. So it goes up and down, and that's what you see is light and dark blue, but if you go in the transverse direction, it's translation invariant. So you get these stripes of dark and bright. But then as people turned on the magnetic field more strongly, they realized you get these lattices, and they were interpreted as lattices of skyrmions. So the picture of a skyrmion, these are both options. So you have a vector which is on the 2-sphere, and it points up everywhere at infinity, that's the vacuum, and it points down in the middle of the configuration, and in between it can rotate in a number of ways. It can either just go straight from up to down, that's what's called the Neal skyrmion on the right, or it can do so by rotating, as it were, sideways, or transverse to the direction of travel radially outwards. That's called a Bloch skyrmion, and that's the kind of vortex-like picture that I'll be focusing on. So that's the kind of skyrmion that I'll be largely talking about. Whereas these helical structures, they're in a real-life simulation on a car park in South Africa over there, but that's another way. That was this linear structures that you saw. And the model, mathematical model, is, as I say, is in this case in the plane. So it's a map from the plane into the 2-sphere, and it has an energy expression that you want to minimize to find these configurations. And it always has a Dirichlet term. That's kind of standard in these models. It has some terms that do not depend on derivatives, and one is characteristic of the material, an anisotropy term, and one depends on an external magnetic field, the Zeeman term. But the term that makes these models work and interesting and has given them this chiral name is this term here, which takes this parallelization tensor. That's a matrix of constants, really, and contracts it with this Lifshitz tensor, it's sometimes called. So that term, at first sight looks slightly odd, but I hope I give you sort of a perspective of that makes that seem more natural. From the point of view of skyrmions, you're probably all familiar with the kind of Derrick scaling argument. This is the scale invariant term. These integrals of functions integrate to something that's scaled with length squared. So normally you would therefore expect any finite energy structure to collapse under scaling. But this term is called first order derivatives. So that's still linear in the scaling. It looks like it will still collapse, but the point is this term can be negative. So then you've got a parabola that has a minimum away from zero scale, and that's the trick. Actually, it's very odd. This is called skyrmions because Skyrm's trick was to put a fourth order derivative term here. So there's something that's inverse in length and then stops it from scaling in that way, from collapsing. So Skyrm's trick actually doesn't apply here. This is another trick by linear scaling with a negative coefficient. But that's a way of stabilizing finite energy configurations. And that's what I'm interested in. And if you take this to be of a particular simple form, essentially it's a 2 by 3 matrix with the identity at the top and 0 down at the bottom, then you get this m dot curl m. And that's the term I'll focus on, although most of what I say generalizes to other models as well. I'm going to do something that may not be needed in this context, but this relates to what Melanie was talking about. Take everything away and look at the simplest model, which has only got the Dirichlet term. And in that case, as Melanie said, the minimizers are given as holomorphic or anti-holomorphic functions. Now that can be seen, that inequality of the energy by the area of the pullback area form can be seen more explicitly, and I need that precise form, so I'll just quickly do it in this case, and then I'll use it in the Skyrm model later. So reminder, if you just take the gradient squared, then and you've got the boundary condition that at infinity everything points up, you essentially have a map from 2-sphere to 2-sphere with a degree, and the degree can be computed by this pullback of the area form, and it's 4 pi times an integer, and the energy is bounded by that pullback and by a simple completion of square arguments. So again, most of you will have seen that if you take that energy, that Dirichlet energy, and you use the fact of orthogonality of m with its derivative, then it's equal to this square, and you take away the cross term, which is precisely the degree. So it's bounded by the degree, and the equality arises precisely if this first order equation is satisfied. And some in the kind of solitons community is often called the Bogomolny equation, but it implies the variational equations, that's the point. And if you write it in terms of stereographic coordinates, it simply becomes the statement that the stereographic image of this is either holomorphic or anti-holomorphic. And it's important that in this model, I had 2 signs here. So there was a modulus, because I can choose a sign here, and depending on which sign I get, I've got a holomorphic or anti-holomorphic function. One gives me positive degree, the other one negative. Now, then you can write down solutions as rational maps. And if you plot the energy, they have these bumps. So they're kind of a nice model of energy concentrated in regions, and this is an example of a topological soliton in some language. Now, why is this relevant to this magnetic Skyrm model, which looks very different? So this obviously is the model that I said I'll talk about, and now I'm going to concentrate on one particular version of this, where the combination, and I'm sorry, I thought I switched from m to n everywhere, but clearly not there. But all the m's are n's, okay? So the particular combination of Zeeman and anisotropy, which is just a perfect square, so it's very simple. In that case, this model has some amazing properties. So let me focus on that for a second. So I've got this perfect square as a potential, which is just the sum of anisotropy and Zeeman. The variational equation is what it is, and actually, I find, if you include the time derivative, I always find it remarkable that if you include time here, that's like the material derivative of m. So it has a striking similarity, I find, to Navier-Stokes equation for a fluid flow with unit speed, because m is of unit length. I don't think that's exploited very much, and I won't exploit it myself, but I always find that something that intrigues me. But moving on, so the variational equation is hard. You have to solve that numerically, and I will. In fact, I'll use Tom's simulation of them. But there's something surprising about this, and I'll do this quite quickly, but this is quite an important slide. So if you introduce a covariant derivative, which this is sometimes called the chiral derivative, it's quite standard in this community, but if you sort of use the language of gauge theory, so you think of this magnetization field as a section of an adjoint bundle to a principal SO3 bundle over the plane. And the connection is that I need for this is externally fixed. So it's not a Young-Mills theory of a dynamical field, which is the gauge field. I fix it, and the connection I need to fix is a famous connection. It's called Cartan's helical staircase connection. It's something that Cartan studied to illustrate torsion. And so if with that connection I write down the covariant derivative, and then I write down a gauge sigma model of a rather simple form. So these are the covariant versions of the derivative squared. And I add a term which is very natural, which is the curvature of this connection, which is Lie algebra values. So my Lie algebra in this case is just R3 with the cross product. And I can take an inner product of that with the magnetization field itself. That's a 2 form, which is now a scalar because I've contracted it with the magnetization field. In gauge theory, it's a very natural thing to do. Both are adjoint valued, and I get a 2 form, I can add that. And lo and behold, if you just use identities of gauge theories, that is the magnetic skyrm model, just written as a gauge theory. So you just go through the algebra and use some identities, and you arrive at this equality. And that gives an interesting perspective. Namely, if you, well, first of all, there's a piece of analysis here. That model, as you know from the CPU, the pure Dirichlet model, the solutions have this polynomial fall-off, and there's issues with the boundary to get well-defined variational problems, which was addressed by Döring and Melchior. So they said, actually, what you should do in this model, you should really look at M minus E3. But E3 is a vacuum, so you should sort of M minus a vacuum rather than just M itself. And that turns out, that trick of saying, well, that's actually a better model, that turns out to be quite useful here as well. So if I add this term, it looks very nice in this gauge formulation. It's the integral of the connection dotted with the magnetization vector and integrated around infinity. That's a natural boundary term. If I do that, the energy is simply a square plus a degree. So it now has exactly the property of the pure Dirichlet model in a covariant version. So this is the square that we had before. And the chirality comes in by forcing you to only have one sign. So now you have no choice. There's not a plus minus here. It's only bounded by the actual degree, no modulus. Okay, so that's surprising, but if I had chosen a plus f here, I would have got the other model. And so there's a choice of chirality has to be made. I've made my choice, and with that choice, I again have a first order equation which, when are satisfied, minimizes the degree, and you can check that that first order equation implies the second order equation. In other words, I can just solve this equation, and I have solutions of this model, minimizers that attain the bound on the energy which is set topologically. There's lots of subtleties here which I'm skipping over. This degree may not be well defined. These are not maps that necessarily point in the same direction at infinity, so that's part of the kind of discussion. But you can now use, again, tricks from gauge theory to write this helical staircase connection in terms of an SL to C valued map. So that's writing it as a pure gauge, if you like. And if you write it like that, you can use that formulation to actually solve the equation explicitly. And I won't go through the details of that. It's just algebra and solving very simple ODEs. But so the miracle is the solution, remember, for the pure Dirichlet model was holomorphic or anti-holomorphic. Now the solutions are only holomorphic plus a fixed anti-holomorphic part. So that's the bit that you cannot choose. It's the parameter kappa was in the model. It's not 0. You have to have that. So solutions are, for example, z bar plus a polynomial. Those are nice solutions. And you might think that's a very minor change, but actually it's quite, I was quite struck how little is known about functions of this form, z bar plus a polynomial in z. Even counting the number of zeros is hard. People don't know that. So there's a bound on the number of zeros of such functions, but polynomial is trivial to find the number of zeros, but here that's not known. So that makes the kind of study of these as skyrmions interesting. So it gives you a simple recipe. You just pick your favorite holomorphic function, you add z bar, you apply inverse stratigraphic projection, and you get your favorite Christmas card with a skyrmion. So that's what back then we did. The simplest was actually known. So this solution, when you only have z bar, that had been discovered independently by Düring and Melchior in a paper. But when you add z, well, if you add a constant, you just translate the skyrmion. If you add z with a coefficient that's bigger than the one of z bar, you actually get an anti-skyrmion. And the halfway point, when you add them with equal, is the helix. So you get solutions to the skyrmion, and then it becomes a helix which has degree 0, and then it becomes an anti-skyrmion when the holomorphic part dominates. So there's a whole study there. If you add z squared, you actually get 3 bumps. There's a kind of anti-skyrmion in the middle. So it's quite kind of intricate, and I'm not going to switch my illustration of these. At the moment, I'm showing you the actual arrows and then a plot of energy density, but that gets hard to read as the degree increases. So there's a different convention. Actually, sorry, there's one other that's quite important I need to tell you. This is a kind of skyrmion loop. So if you just add 1 over z, now they both have the same radial dependence. So this is actually an axially symmetric configuration, and it has degree 0. So it's this kind of helix, but wound in a circle. That's called skyrmionium. So that's a degree 0 stable configuration, which is actually in this kind of physics of skyrmions is almost the most important configuration of all. It's more important than the skyrmion. It's got degree 0, but it's a stable soliton. So it's quite surprising. Now, as I said, I'm going to switch my illustration. And one thing I did with Philip and various people in Jülich was to take these holomorphic configurations, which only work at a particular value of coupling. So they're not, if you give me a physical model, the coupling constants will be different. And generically, at physical couplings, these solutions are not solutions, but you have these exponentially localized solutions. But one thing that's quite difficult is to find interesting solutions of degree 612, or any number you choose. But with this holomorphic ones, it's easy to write down solutions of degree 612, and you can take them as a starting point in a numerical search. So that's what we did, and I just wanted to, so these are, on the left-hand side, are the initial conditions just given by the inverse powers of z, and then we let it evolve. And there's this skyrmionium, and this picture I'm really just showing you for the new convention. So black is the magnetization pointing up, white is pointing down, and in between you've got a region where n goes from up to down, it goes through the equator, and on the equator the direction of the remaining vector, which is the n1 and 2 component, it rotates through the color sphere. So this is the Bloch color sphere to map them. So you always have color on the edges of where black and white meet, and that's where it encodes the way the field n1 and 2 changes. And so one thing that's quite striking is obviously here you've got a vacuum in the middle, and then you have an anti-vacuum, so you go to the top of the sphere on a white ring, and then go back down to the vacuum. And between white and black, there's 2 magnetic walls. So that's the terminology in the physics literature, where white and black meet. The magnetization goes through the equator, and that's where, on the equator, that's called a magnetic wall. So and what you see from these pictures is that these magnetic walls are very interesting. There are the boundaries of the white and the black, and you see that they develop these kinks. So they have these sharp curvatures, and these kinks actually begin to they're actually the degree -1 in this case. They are actually the degree. This is degree 0, and each kink adds you 1 degree. So these are intriguing pictures, and I'll say a bit more, but with other solutions, if you take a different rational map and you relax, you get these sections through pomegranates. So these are these bubbles stuck together, and again, there's whites and blacks, and in between there's walls. This time without kink. So one thing that that's intrigued me and other people, and we have not made much progress, is to begin to think of these skyrmions as a theory of these walls, of these magnetic walls with kinks on them. It's almost a kind of string theory of skyrmions. So you have these loops in space, and I think there's something there, but it's quite hard to make that precise. But I'll just show you why that's interesting, even from a basic point of view. Well, first of all, these things are seen. So these solutions have been observed in transmission electron pictures. So these are not just numerical artifacts, but skyrmionium and this degree 1 combination of two skyrmioniums, that they're known. But so this is not a skyrmion, this is a cowhide, but it's got black and white. And I'm drawing these regions, these magnetic walls in blue. And when you have the plane, obviously curves have an orientation. If I choose an orientation, then there's a preferred orientation. But when I insist that my curves are orientated by having black on the left, then some of them will become positive, i.e. the same as the geometric orientation, and some of them will become negative. So they become signed. And it's quite an easy calculation to check that if I take on each wall the vector n1, n2, which is on the sphere, because at that point n3 is 0, n1 squared plus n2 squared is, on the circle is 1, so that it's a vector on the sphere. So that's got a winding on each of these closed loops. The winding number of the whole skyrmion field is just the sum of these windings, weighted with the sign, so with the right sign of the wall. Okay, so I've chosen the orientation when I go around with the black on the left. Now, to get closer to the physics, it's not so important to think of the direction of n1 and 2 itself, but in relation to the tangent vector to the curve. So that's what I call psi here. So if red is my actual vector n1 and 2, and blue is the tangent vector, then the field psi is the one that you really want to focus on, I claim. So the field psi is kind of the direction of n relative to the geometrical tangent vector. So now the number of kinks is the number of the windings in n1 and 2 minus the winding of the curve itself. That's always plus or minus 1. So I've taken that away, and that gives me the number of kinks. So each, if I just go around geometrically, that's not a kink. So that's the skyrmionium. If I wind more or less, that manifests itself as a kink. That's the reason why I take away the geometrical information. And now the topological charge is the sum of the kinks, and then you add or take away one, depending whether it's a positive or negative wall. And you can also, so you can now play this game. You look at these now, and so that's got one negative and one positive wall. One's black is on the left and one's black is on the right, and they cancel. So that's degree 0. Here I've got the same picture, but now with the kink, so that's got degree 1. Here I've got 2 positive walls and 1 negative wall, so that's got degree 1. So that's quite a good way of thinking of these, and then you add kinks to them. So that's quite a good way of thinking of these, it seems. And something I won't discuss here, but if you work out the energy on the wall, so you take this field psi, which is the direction of n1 and 2 relative to the tangent vector, and you just work out what it is on the wall, it's a sine-Gordon model on the wall. And and this cos psi term tells you that comes purely from the DMI term. And it says that on the wall, if it's a positive wall, the angle wants to align with the tangent vector to make that angle 0. And if it's negative, it wants to anti-align. Those are the requirements. So there's potentially a theory of the shape of these walls that one could study, but this is only the theory on the wall, so it doesn't tell you the shape of the wall, for example, and that would be a difficult and interesting thing to study. Okay, so it's time I get on to the dynamics. I haven't talked about dynamics. So this was all about the static configurations, and I showed you that there's a special coupling where you have exact solutions, and you can use that to study a whole kind of universe of solutions. And when you do that, you come across this interpretation in terms of walls and kinks on walls. And that's, I think, an interesting view on static solutions. But I'm slightly over halfway, so it's time to start talking about dynamics. But are there any questions on statics? Not, then I'll move on. And so the full dynamics in this model is quite complicated. So there's the dynamics that comes from the interaction of the magnetic magnetization field with itself, and there's two types. One, lambda Lifshitz, and then the Gilbert part. And then there's also the response of the dynamics to external currents, which actually technologically is even more important. And there's a lot of literature on that. And I've thought about this, and I think it's very interesting, but I won't talk about that in this talk. So there's this talk here is the effect of adding a current to the picture. And there's actually two bits to this. And I've written down the spin transfer talk, and there's a spin orbit talk as well. It doesn't have derivatives in it, and that's a whole interesting story, but I'll skip that. So I'm interested in these two terms. And the traditional way in the physics literature to write this is to have the time derivative on both sides, which is slightly confusing, but you can fix that by bringing all the time derivatives to one side. So now it's time evolution, which has the H effective, so that's the terminology that's used in this field, is an effective magnetic field, but really it's there. That's the formula. So that's the variation of the energy with respect to the magnetization. That's the term that I call H effective, and then there's the term M cross H effective. And the term have coefficients gamma and alpha, and alpha is 0, means you only have this first term with the cross term. That's the time evolution which preserves the energy. And the second term is a term that minimizes the energy. It's actually the gradient flow. So the first term is a Hamiltonian flow, and I'm going to call that symplectic gradient, because in both cases you have one function, which is the energy. You have its differential, which is the one form. Then there's two ways of turning that into a vector to define a flow. One is by the symplectic form, and the other one is by the metric, if you have either of those. And in this case, both are used. So it's a linear combination of the symplectic and the metric gradient that you can compute. And I want to sort of put that into a slightly more sort of geometrical picture, which is to think of this evolution as a time evolution on the space of all maps from plane to sphere. That's an infinite dimensional manifold, and that manifold actually has a metric structure and a symplectic structure, both inherited from the metric and symplectic structure on the two spheres. So I've given some formulae for that. So del M is meant to be a one form in the space of all functions, but the kind of explicit form is there. So that's, if you've got tangent vectors, you just integrate the dot product over space, and that would be the inner product of them. Of course, tangent vectors have to do a particular thing in this case, but that's very standard. Equally, the symplectic form is looks a bit like the area form again, and it's of course related to that. The area form is the symplectic form on the two sphere, and this is the pullback, or it's the integral of that pullback over the plane. And so another property is that these metric and symplectic structures on the two sphere are related by a complex structure on the two sphere, and that also happens in this infinite dimensional case. So there's a Kähler property which relates symplectic and metric structure. So why is this useful? So this is just a bit of fun now. This is where technology has got slightly more complicated than I thought. But that's just, if you have a symplectic so on the right is a purely symplectic flow on a two sphere. So you take the height function as your energy, then on the right-hand side, that's a symplectic flow, which preserves the height. In the middle, that's the gradient flow, where you just go straight down the sphere because you minimize the height. And on the left, that's the combination of symplectic and metric flow, which I'm talking about. So it has the Hamiltonian flow but it also drops down the sphere in minimizing the energy. So how can one write these equations that I gave you, these Landau-Lifshitz-Gilbert equations, in this way? I'm going to do this in a sort of slightly physicsy way. The physics literature on this time evolution uses an idea called a collective coordinates, which is very common in physics, where you say, well, this is an infinite dimensional problem, which we cannot easily solve. You can solve it numerically, but if you try to get some understanding, you try to isolate the important degrees of freedom at the energy range that you're interested in. And in some cases, you can do that exactly. So there are solitons called Bogomolny solitons, where you can write down an exact space of ecstatic solutions and study the flow in that space under second-order dynamics. That's a very popular and much explored area in the study of monopole dynamics, vortex dynamics. This is first-order dynamics. So any static solution, if you take that as an initial condition, it would just stay, because it's a static solution. So that's not, static solutions don't give you interesting collective coordinates. But there's other ways of arguing why certain families of configurations are interesting. And there mustn't be static solutions. There must generalize a static solution. And then the idea is, and these are parameterized by these xi's. So xi is a set of collective coordinates. I'll give you some examples in a minute that parameterize a bunch of solutions, configurations rather, not solutions, that I want to study. And then I assume that the time evolution is only through the variation of these collective coordinates. So that's the assumption, which one then has to justify that gives a good approximation. So a simple example would be time translation. Again, in this case, that wouldn't be very interesting, but you could imagine asking, well, what happens? In fact, when you apply current, that becomes a very good thing. So if you have a solution, you can put it anywhere in the plane. You can say, well, let's assume that position in the plane now varies as you apply the current. When you plug that in with the current put on, you get eventually an equation called the Thiele equation. So this collective coordinate approximation in this context is called the Thiele approximation. So it goes back to the last millennium. And this is a different sort of geometrical take on that. Okay, so I assume that these collective coordinates evolve in time in a way that I don't yet know. So I'm just assuming a time dependence. That means all the time derivatives can now be expressed in terms of time derivatives of the xi dots. And I plug that in here, and I plug that into these equations, and I project onto the tangent vectors in the xi directions. When you do that, you get an induced metric and symplectic structure on this space of collective coordinates. You can just restrict to this finite dimensional, maybe it's a submanifold, let's assume it is, you restrict to that, and then you get a metric matrix in these coordinates and a symplectic matrix in these coordinates. And the algebra of projecting the equations of motion onto the tangent space to that manifold gives you this equation. And if you know, the gradient flow equation is precisely that with no omega here. So it's a metric times the time derivative of the coordinates on the manifold gives you the naive gradient of the function with respect to the coordinates. And equally, if you have a symplectic flow, you use the symplectic matrix to lower the index, if you like. So this collective coordinate picture is a linear combination of symplectic and gradient flow. And I think, so a question to this community, that equation I don't see studied very much. I looked, there's a thing called metriplectic flows, and that's exactly this linear combination of metric and symplectic structures, but it's not been studied much. It's interesting that if you didn't have the metric part, only the symplectic, then there's an issue of whether this can be inverted, because a two-form, the symplectic structure is a non-degenerate two-form, but when you restrict it to a submanifold, it may not be, it may lose the non-degeneracy. And so the inversion then doesn't work. That can't happen with a metric. And the good thing is, if you have this linear combination of metric and symplectic, it also can't go wrong. You can always invert. That's a simple piece of linear algebra. And so this is actually quite a nice sort of regularization of a symplectic flow, but it's physically what happens. So that's my kind of first general picture, that one should think of this Landau-Lifshitz-Gilbert equation as a combination of metric and symplectic flow. Now, here's a skyrmion. So let's illustrate this with some simple example. That's a skyrmion which has got the anti-vacuum in the middle, the vacuum outside, and then it has this magnetic wall, one single magnetic wall of negative sign, because if you now have black on your left, you're traveling clockwise and mathematically negative. So that's a negative wall, and the skyrmion has degree -1. So that all fits together well. And you've got these colors going around. And if you now, so we have to now pick some collective coordinates. And the choice that was also studied in the literature, this is not our idea, but the one that's obvious from the point of view of this being a perturbation of the Dirichlet model. And the Dirichlet model, scale and rotating the magnetization vector are zero modes. They don't cost you any energy. The energy doesn't change if you scale, and the energy doesn't change if you rotate. In the magnetic skyrmion model, both of these cost energy. The DMI term kills the scale invariance, and it kills the independent rotation in space and on the target space. You have to do it together to have the symmetry of that model. But if you then we're interested in something which is not a zero mode, because that would just give you another solution, therefore you wouldn't evolve. So what we do is we take this and we rotate the phases and we pump up the scale. Those are two obvious things you can try, and you can ask what happens if you do that, and the answer is this. So you get a breathing motion, and I'll probably have to run this for a while. So, I mean, you can see that the scale changes. That's very obvious from the picture. But if you look at the colors around the magnetic wall, you can see that they wobble back and forth. Okay? So this is a motion of breathing where a scale change comes along with a change in the magnetization on the wall, and then it flips back. So these two are in sync. So the question is, can you understand this in terms of a simple collective coordinate model? And the answer is that works very well. In fact, in almost too simple a way. So if you, in this Borgomoni limit, I just use that because it's easy to write things down. The skyrmion is simply Z bar. The scale is dividing this by a scaling rho, and the phase is multiplying everything by a phase gamma. Okay? So that's the configuration that I plug into my energy in my symplectic form, and I find that the two coordinates rho and gamma are just symplectic conjugate pairs. And the energy function is a quadratic function. And its contours are, in this very simple model, are solutions. Right? They are, because I've got a two-dimensional model, energy is conserved, so the energy contour is a curve. Those are trajectories of solutions. So they're simply circles. And you can solve the equation, but you don't need to because you've got a conservation law that tells you that. And so you get these circles, but these circles are not at the origin. So they're at along the x-axis. And I've drawn this again on the blackboard here. If you travel around this circle on this x-axis and you ask how does the scale change, it oscillates between the minimal change here and the maximal scale here. So the scale goes between that point, and the phase goes between that maximal phase and the maximal minimal phase here. So that would be the prediction of this collective coordinate model in this theory, and you can check that that's a pretty good approximation to what happens. So when you run this and you extract, so that's the picture on the left is actually extracting the scale and the phase from the model and seeing how it behaves. The picture on the right is the actual numerics, and as you can see, it's not precisely a circle. So the green curve doesn't move exactly in a circle, but it's pretty close to that. So this breathing is definitely a scale and phase rotation, but the details are different. So we haven't quite figured out what that is. Okay, so that's the kind of cartoon of how a skyrmion, an excited skyrmion behaves. It wobbles back and forth in phase and changes its scale, and that's hopefully a sort of simple picture to summarize that discussion. Now, skyrmionium is the other axisymmetric configuration, and we wondered whether that has the same behavior, whether that also just breathes and has a scale, a phase change at the same time. But that is not true, and so the picture is much more complicated here. And if you, again, I'll let you look at that. even have time to ask the audience, what do you think is happening here? So it still breathes, the scale goes up and down, but perhaps you can see what's, well, first of all, I mean, it's kind of hypnotic, quite fun to look at, but first of all, I told you that these are all walls of opposite sides, and the magnetization on the wall, therefore, aligns oppositely. So if you look at the outer wall, it's got exactly the color scheme of the inner wall, but rotated by 180 degrees. That's at the extreme points. So when you start, sorry, not when you start, at the extreme point, the color wheels are exactly opposite. But then they rotate in opposite directions. So the oscillation is still one of scaling, but the phases on the walls now rotate in opposite directions. And that model is one that I'm sort of summarizing here. And again, it brings me back to this idea that the walls and the kinks on the walls are a very good way of thinking about this, that somehow these walls have signs, positive, negative, whether black is on the left or on the right. And when you excite the scaling of the walls, that's a natural motion of these configurations. But their phases will go in one direction or the other, depending on the sign of the wall. Okay, so that's our kind of conclusion. And we haven't been able to write down a model for that, but we would conjecture that this generalizes to higher configurations, where all the walls have infinitesimal scale changes, but the phase on the wall rotates depending on whether it's a positive or negative wall. So as suggested in that cartoon. I'm just going to end with one slide that sort of arises naturally. If you travel around this circle here, the size changes between here and here. So you've got this breathing motion as you go around the circle. You can obviously make this circle bigger, and you still expect that to happen. But at some point, you expect something quite dramatic to happen, which is when you make this is scale 1, this is scale 2. If you go to scale 2, then the scale would go around this circle around the center, but it would hit the scale 0 here. So you would be sending this one, would be sending towards the collapse mode. Equally, if you go to scale 3, there's you go around this circle here. Now the scale is something more complicated. It decreases, and then the angle flips over, and it decreases and increases again. Okay, so the scale motion is quite interesting. And we checked, or Tom rather checked, whether that happens numerically, and it does. Oh, sorry. So this is not yet. So this very short picture, so the left one is what I showed you before, this breathing skyrmion, and the middle one is where you make it exactly the size so that it would hit scale 0 on the other side, and the other one is bigger than that, so it overshoots row 0, and the middle one goes away. So that's in a very short picture, and we can make that more. I'm sure we can work on that.
No, we couldn't see that. That was too quick. Could you say?
I know.
Which was the one that collapsed?
So the middle one.
Which is middle?
So this one here is the one that starts at scale 2, and that does exactly half revolution, and then it hits the origin and dies. And that's this one here, about to disappear. The other one on the far right, that's the one that starts at 3, goes on the other side. It's got a small scale, but then it comes back up with a.
And the left one is the one you talked about earlier.
That's right. So that one is.
Go again now. Well, something disappeared in the middle.
Sorry.
It's gone.
Yeah, that's what you expect, because the size, this one here does 1/2 revolution, and then it hits the scale 0, and then the numerics breaks down. And what happens numerically, or sorry, analytically at that point, would be a question to the audience. But you can fire this directly into its demise by starting it off at the right scale. And that's the CP1 model has got this question of whether what happens when you give it second order dynamics towards scale 0, and this has got a version of that, but you started off at a different scale, and then it rotates round to scale 0. Right, I'm just 19 seconds over time, so I'll leave you with these conclusions and stop. Thank you.
Thank you for the very nice talk. We just had a question. I think the 45 minutes is including questions, actually.
Oh my God. Okay.
I didn't. Yes. Anyway.
I didn't understand this collective coordinates business. I mean, later you showed examples where you apparently make specific choices of these collective coordinates. So what's that got to do with the actual PDE?
Well, it's a good question. So in other models, there's various ways of arguing how you can construct collective coordinates, and then to prove that motion on these collective coordinates approximates the time evolution well. We are way miles from that. So this is at the moment a random guess. I mean, it's guided by physics or guided by what the simulation shows of how these things move by trying to understand it in terms of a finite dimensional set of collective coordinates. Then you compute the induced dynamics, and in this case it's just scale and phase of the skyrmion, and we find it agrees well. For the skyrmion it works well. And now the question to the analytical community would be to show that actually you can show that when you have the motion on the collective coordinate and you've got the motion of the precise exact solution, that when you start close, they stay close. And that's been shown, for example, for monopoles, that there's a proof like that by David Stewart. In vortices, I think there's some results of that nature. But in this model, we are literally in the state of just trying to invent the right collective coordinates.
Okay. Thank you. And let's thank the speaker again.